So I'm happy to be here and to share with you this. Since I have only half an hour and you are all tired, etc., I will not go into so much details, I would say technical details, but essentially discuss a number of, because Ron this morning discussed issue about human-robot interactions in some aspects, also Pedro. So I'll try to give a complementary view, essentially, of what is it inside the system and what are the challenges somehow. And then we can discuss a number of issues, etc. Why is it pertinent or not to have human interacting with robots? Are these robots useful and pertinent? Will people like it, etc.? This is a question to be discussed. So, however, thinking about human and robot collaboration, like it's mentioned here, raises a number of questions concerning not only the physical interaction between the human and robot, but also the decisions, which decisions the robot should take somehow, which means in terms of planning, in terms of interpreting correctly what is happening in the scene, etc., etc. And having the human and the robot in the system, we discussed about this yesterday also, about the human in the loop somehow. I'm speaking here more about human in the loop, but also in the scene, sharing the task and the space with the robot. This takes us to something from this autonomous robot model to the collaborative robot model. Okay? So for a number of years, I would say, the dream of the robotics people was, and the challenge, which is still true today, was this one. The robot was there alone, like this, for example, or other kind of robots. We build it, we think about it as very capable. We want it to be very capable. We want it to be very intelligent, okay? We wanted to give to it a task, a goal, a high-level goal, not the detailed things, because we want the robot to be autonomous and do it, and the robot will do the job. Okay? It can be ready for a new adventure, or it can die during the mission, depends on the mission and the robot, etc. But that was it. Okay? And it's still very interesting, and it is still important, and we are not yet in it. Okay? It was this kind of robot. Okay, the hero. It goes, does the work, finished. But there are other kinds of robots. And now I have to tell you something. Yesterday, don't tell it to George and to Lakmal. I went to, yesterday morning, I went to Louvre, Abu Dhabi. Okay? And there is, I've seen this. Okay? They are preparing an exhibition concerning this guy. And the title of the exhibition is When Art Met Cinema. But there is something else. When cinema, or when art, I don't know, will meet robotics. And this took me to an old video that I had, that I will show you again because I'm obliged, which is this one. This one I'm showing essentially to students in the first year when they were discussing about this issue, these challenges of human-robot interactions. And then and I was saying this, I'm saying this each year in the first course. When it comes to human-machine interaction, we had the forerunner. And this forerunner is this guy. Okay? Why? Look at this. Sorry. I should put the sound. It's coming. No, sorry. So this is an autonomous mobile robot, okay? Service robot, coming to serve a person. And you will see now all what we should not do, okay? Look, we impose to the human and we tell the human what the robot will do, okay? Okay, we explain to the human in detail what the robot will do, okay? We calibrate the human, not the robot, okay? Then you have the engineers, very proud. Always, engineers are always very proud. Okay? Okay? They start, everything goes well. Sequence of sequences started. So there are a number of steps going, one step, different tasks, the variety of tasks. There is some kind of high-level protocol running there, okay? The human is surprised. He has no initiative, okay? He is really surprised, and it's the machine who imposes the rhythm, okay? The machine imposes the rhythm to the human, okay? Human is surprised a little, okay? Look, it doesn't know exactly what will happen. It is completely passive. The human is passive here and complies with the robot, okay? The robot, I say. This is another kind of task, a variety of tasks. There are a number of creative mechanisms done here and there, okay? Task-specific things. Engineers are always proud, okay? Sometimes speed is not that good, okay? It could sometimes not that adequate to have high speed, because again, who asked for the speed? And reset. We have a reset. Okay? They already had a reset. Okay? Now it started again. Okay? Calibration problem. Okay? The high-level task is always working well. The planner is very happy. The details we don't know. Okay? The guy feels less and less satisfied. Less and less, he says, what am I here? So the guy is imprisoned in the system, okay? Is in jail with the system. Perception is needed, not working very well. We know about this a little, okay? The engineer is doing some things. It will happen what it should happen, and it happens, okay? So part of the task is okay, but one parameter is defective, and this is what you have. Okay, high-level task is good. Okay, high-level plan is very good, rigid sequence, and now, of course, we need this. Okay, if not, it's not finished. But again, now the machine is autonomous, really autonomous. But well, well. Okay, so it's a little long, but in fact, what I liked in this is that first, it's modern times for those who don't recognize it. Shot in 1932. Okay. Premiere was in August 35, okay, no, sorry, in 36. And you have here a number of things we are working on in human-robot interaction, okay? Proxemic interaction, okay, very close interaction between the human and the robot. Initiative taking, who takes the initiative? Okay, the human or the machine, okay? Adaptation to human, okay? The rhythm should be imposed by the human, not by the machine, okay? The restart should be imposed by the human, but not by the machine, etc., etc. The pertinence of choices, okay? The pertinence of decision. The right decision at the right moment at the right place, okay? Based on good interpretation of what is happening, etc. And of course, reliability, safety, fault tolerance, etc. And you have all this in this video, okay? 1932, okay? So, here we are, okay, and this helped me simply to state this, okay. The cognitive and interactive robot, okay, it's really I would say a scientific challenge. Already 8 minutes, okay, which needs cognitive and interactive abilities, and we'll go to some of them that will allow the robot to be pertinent, to be transparent and predictable in what it will do, to be legible, okay? The human should be able to interpret the intentions of the robot beforehand, to be acceptable, because it could be legible and not acceptable. We have to pay attention to this. Behaviors, in order to perform collaborative tasks with the human. Of course, the applications are the service and the assistant robot, or the teammate robot in the factory, etc., etc., etc. Now, for young researchers, because we're assuming we have young researchers here, okay, there are some good news, okay? We have done very little, okay? There is a lot to do, okay? And we have just started to scratch. We are just here, okay? Just scratching a little the surface of the things, okay? There is a lot of things to do, a lot of things to discuss and to refine in this human-robot collaboration in order really to achieve what we want with this robot. Now, I'm speaking about decision, but still we have to say, the robots that will do physical interaction, direct interaction with the robot, they start to exist today. Okay? They exist. This one is able to do this. You all know, I think, this video that are very popular, particularly this one. Okay? This is physical interaction, and it's done very well. Okay? This guy is Sami Adadin, who those who do not know. Okay? He is still able to answer simple questions. Okay? After this, okay, I know him very well. What is his professor today at TUM, and he's still he survived this. So physical robot interaction is possible today. Okay, decision is an issue. Okay, perception is an issue, and there are a number of issues to look at there. And in fact, there is a need to develop an integrative approach for all these aspects linked to the fact that of this ability of the robot to perform joint activity or with the human. Okay, so since I will already 11 minutes, I will switch. I will accelerate a little. I will skip the sources of inspiration that guides this. It goes from multi-agent and BDI and dialogue work, development psychology. There is also a community that is very interesting that is called the Joint Action Community, which are essentially sociologists and philosophers working on joint action between humans. Okay? And we are more and more exchanging with them. In fact, we have created a series of workshops. We have already 12 workshops organized and located in different places where we discuss with these people this issue of what does it mean, how we can transfer to the human-robot joint action what is done in human, what they study and what they know in human-human action. Because what we know about joint action, and this is a definition coming from them, between humans. Okay? It's an activity where several humans coordinate their activity in order to bring about a change in the environment. And this means a number of mechanisms behind this. There are ways to make this fluent and feasible, and ways to also to make it very bad. Okay? And because it can go bad, even between humans. You know very well when you interact with humans that you have good collaborators and bad collaborators. You can go well because there are a number of signals that will be exchanged. There are a number of duties in both collaborators engaged in a joint action, etc. And we are trying to look at what we can do if we replace one of them by a robot. But the replacement is not simply having the same. Human and robot will not be at the same level. Humans are at the same level. Human and robot are not at the same level. We should be clear about this. Okay? We are not replacing this joint action between human and robot in the same way. We are looking at what joint action between human is operating and try to get from it what will be necessary to have the robot do its work and be a slave. We want the robot to be a slave and help the human and not the equivalent or taking a decision instead or in place of the human. And now, okay, I have the time, I will go to some of these decisional issues, some of the capabilities that we have identified that could help the robot enter the field of human-robot interaction. There are essentially two levels. You have the high level, the hierarchy, I would say, to simplify. Okay, this is work done also by philosophers working on these aspects on human-human joint action, where they also distinguish the two levels. We call it decisional level. They call it differently. They call it the distal. Okay, and then we have the low level, which is more the shared, proximal, the execution, the context-based refinement, where you perform things. And sometimes you collaborate, sometimes you simply coordinate. So I will give some examples. I will not go into details. There are a number of issues that are very important when you do the joint action, which is what we called self-order distinction and also self-order manifestness. Each of the partners of a joint action should manifest its intention, should help the other do the work, using a number of mechanisms like the joint attention, working together to something, the facilitation, how to facilitate the work of the other. And it means also that you have a number of things. If not, you cannot do it. You can do joint activity with humans only if you share a background of knowledge, okay? And you share also a good understanding of what happens in front of you, of the task, okay? And I will go to some of this as an examples now, okay? So what I want, and now I will first stay at level that is really, I would say, problem statement, because I think it's more interesting. For the rest, you can find it. Okay? What is the problem statement? Okay? This was how we were doing before. You have a robot, you have the human, you are a good roboticist, okay? And so you say, okay, the robot sees the scene, sees the human, observes the human, okay? And the robot is endowed with these capabilities. It is endowed with the situation assessment module. It has a high-level task planner. It has a very good geometric motion planner and an action planner. And it receives a goal. It builds the current state of the environment and of the task based on this perception. And it has a model of its own actions, how its actions could be performed. It knows also at geometric level its kinematics and its dynamics, its own dynamics, the robot, okay? And build all this, it builds the plan. Okay, I'll do this and this and this and this. This is not sufficient. This is not sufficient if the human and the robot have to work together. Because what we need to take into account is what I call models. The robot should take into account the fact that the human is an observer. Okay? The robot should take into account that the human is observing the scene, is observing the robot doing the things. Okay? This is very important. The robot should take into account to model the human as an actor, because the human will act in the scene. Okay? So it needs to have a model of this. Okay? And it's very, very important. The model could be manipulation, could be movement, hands, could be signals that are exchanged, multimodal signals that could be exchanged, also identity, etc., etc. The robot should also take into account that the human is an evaluator. The human is evaluating what is happening. It's a jury. The robot has a jury with it. Okay? Doesn't need the international jury. Already when it is doing interaction, the human is judging it. Okay? And this also can be used to build the model. Okay? It means that the human will judge if the thing what the robot is doing is visible, if it is legible, if it is acceptable or not, and it is conformant to a number of, I would say, norms and ways of doing things. Okay? And this is why we need theory of mind. Okay? We need theory of mind because the robot should estimate the state of mind of the human, not everything, but around the task, around itself, and around what is happening. Not about the fact that this morning he is angry because he had a problem with his children or something. This is not the problem. It's only linked to the task and what they have to do together. And it's all this that we need to have in a future interactive robot system. Okay? Now, let's look at what does it mean if we go back to the scheme that I have drawn before. Okay? Same, you have the human, you have the robot. Now you have a shared goal. You have to share the goal before everything. Okay? And then the robot will build the current state, estimate the current state of what is happening, but this is not enough. It should also have all the past events that happened before. Okay? Not only the state, but what happened before. It is important to do a number of things, to have a robot again pertinent. Okay? It needs to estimate what the human is seeing from the scene. This is what we call the perspective taking. The robot should estimate what the human is seeing in the scene. And also what the human have seen before and have lived before somehow, past events. Of course, I'm drawing the big scheme. Okay? And then the robot should again have the set of actions it is able to do, but it needs also to know what the human can do. Okay? The actions of the human should be also modeled from the robot point of view. It also needs to know the joint action protocols. I mentioned these notions of joint action protocols, how joint action is happening, and what are the rules and mechanisms of joint action protocols. It needs also to know its own kinematics, like before, but it needs also to know those of the human. Okay. The robot should estimate the kinematics of the human if it has to perform a task with the human. Okay? And from the human point of view, the robot should have a model of the estimation of the human knowledge, okay, about its own actions, about its own abilities. Okay? It is not enough for the robot to know what it knows about itself and the human, but also what it estimates the human knows about it. Okay? And this notion of common ground is key. It should be clear when you build a system what is the common ground, what is known before in terms of task, but also in terms of abilities from the human and from the robot. And then this is the notion of the robot as evaluator. You have the notion of preferences, etc. So and then and only then you can try, the robot could try to build a pertinent plan. Okay? Taking all this into account. Okay, so again, I'm drawing the large scheme. Then we are contributing here and there in this scheme. And here I try to put the color of different things. Here are all the models that are needed for the robot as observer. Here are all what is needed in green, in blue, sorry, for the human as actor. And this is what is needed for the human as evaluator. And the model is not finished. But however, it gives you an idea of the large scheme. So since I have only 7 minutes, now I will go to detail and show you some examples of what we have done. So this scheme has not been built the first day. It took us a long time to think about it and to come with it. But I think this scheme is now what supports what we are doing in my team concerning these different aspects. Okay? And we are working on different levels, on geometric level, planning level, on decision planning level, on physical interaction level, etc. I will give some examples. And we are having, through contribution to projects here and there, and also a thesis, a constructive approach. We are trying to build systems, even imperfect, okay, with a lot of resets, okay, but we are trying to build the system on two aspects. One aspect is essentially, and very important, the situation assessment and interpretation abilities of the robot. And the second one is the synthesis of robot behavior. Okay, two aspects. Do not have now really time to go into the details. So I will give some examples of what we have done, essentially on different aspects. The first one, I'm just giving here for you a number of contributions that we had in this field. We have worked on control architectures. We have worked on task planning. What does it mean to have a task planning in a situation where you share a goal and you share the task? We have worked on what we call human-aware navigation, how the robot should navigate between humans, should navigate in synergy with humans. Also on human-aware manipulation, how robot should move itself to do manipulation with humans. And this seems simple, it's not. Okay. Also, a very important question is the notion of affordances. Okay, how the robot, affordances will help a lot the robot to estimate what to do next. Okay, what the human can do next. Okay, we have worked also on perspective taking that I mentioned before, which is part of theory of mind, what the other sees from the scene. Okay, and we worked also on one task that seems very simple, the handover, which in fact combines a number of these problems in one task. Okay. And we have applied this to different contexts. We had some contributions in robot robot guide, like the one that we have deployed in Schiphol Airport, and went quite well. Also, domestic assistant robot at home. Also, recently, a robot in a mall doing some kind of entertainment and guiding people, etc. And also some kind of work in robot in the workshop with human, the co-bot, so somehow the teammate robot, sharing the task with humans. So, under the hood, there is this. I will not go into these details because I do not have time. What is important here is for each problem, whenever there is some problem to solve here, the decisions are what to do. What to do now, what to do globally for the task. The question is open, very often open. Who is very open? Is it the robot? Is it the human? Okay? Who has the priority? The question is still open. In some situations, it's better if the robot does nothing and leaves the human do. Okay? Where to perform a task? It seems simple, it's not at all. Okay? Very often, when we program our robots, we already choose for them where to perform a task. If we leave this open, it will be a question of decision, and the robot could make the wrong choice. When you can understand that it could be some moment it's the right moment to do, some moment not. And very important, and it appeared incrementally, how there are different ways to do the same task, numerous ways to do. Some are acceptable, pertinent, legible. Most of the others are not. Okay? When you have the robot doing alone a thing, it's not that important. It does what is the result. When you have the human should not be afraid, should be able to interpret, etc. And the how is very important. The motion, for example, is key for the how. And so I've drawn before the large scheme. Now we have developed small models from a number of aspects. So since I have only 5 minutes, I will show you only one result. Yeah, which is this one, and I will stop here. The perspective taking. The perspective the problem is the following. Okay, you have the human, you have the robot, and they are not placed in the same place. So they do not see the environment from the same place, and there are things that could be hidden, etc. And so this makes an issue, because if you want the robot to be pertinent, it should be able to interpret the situation correctly, to compute for itself the relative placement. Where should I put myself so that I can be seen by the human? Where is this object reachable to the human? Is this object visible to human? Etc. All this is very important in terms of perspective. When I perform this grasp, should I leave a grasp for the human to take it also when I do a handover? All this is very important. So we have developed a system that geometrically computes the perspective of the human from the robot point of view. It is a kind of implementation of theory of mind, and we said, okay, we'll test on the robot the classical example that is, this is an exercise for children that is very known by psychologists. We call the Sally and Anne example. Okay? I don't know if you know it. I will recall it very quickly here. You have Sally and Anne, okay, here present, and you play the scene in front of the child, okay? And what you see here, you see Sally putting a ball or a marble, like they say, in the basket, and she leaves, okay? Then Anne takes the ball from the basket and puts it in the box, okay? And Sally comes again, okay? And you ask the boy where Sally will go to take the ball. And until 2 years and a half, the children proudly say, in the box. Okay? For the children, there's only one truth until 2 years and a half. And incrementally, they start to understand that there are different point of views, different perspectives, different beliefs about the same task. And this is what we try to do. After 2 years and a half, it changes. And it seems that for autistic children, it's not true. They continue for a long period of time to have this mixture of perspective. So I will show you an example where the robot here is only observer, robot is red, and you have two persons, we simplify a lot, blue and green, okay? And the robot will try to keep track of what is happening in front of it. Okay? So just see this, and what you see here is two things. You will see the scene running, and you will see on the right, okay, you will see what the robot interprets. Perception is simplified here a lot. You have tags, okay? So when the robot sees a tag, it sees the object and localizes it, okay? And the robot also has a Kinect and is able to track the human. So as you see, it is tracking the human here. What you see on the right here, the robot is building the model of what it has in front of it, okay? The human and the objects. Now, green comes. They are placed almost on the same place. The robot, from his point of view, computes geometrically what is seen and not seen by the human, okay? And builds, you have small balls around this where the objects are from the human point of view. Now, green leaves. Look what is happening. What is happening? Blue will do something in the environment that the robot will track. Okay? Okay? It is, all this is running online. Okay? It takes the object that was there and put it here. Okay? The idea here, you understand, that when green will come back, we'll have some issue. You can see on the right that it takes sometimes several seconds, 1 or 2 seconds, and the robot updates correctly the state. It knows where are the objects, etc. Okay. Now, where green comes back, okay. After a moment, we make them switch so that the robot is sure that they are not speaking to one another. Okay. The robot questions what the human knows about the state and is able to infer that the human sees that the object which was on the right has disappeared, but he is not able to see it from where it is. Okay? So here the robot is building a different belief, divergent belief between its own belief, the belief of green and belief of blue. Okay? And based on this, the robot could interact in a way or another with one or another, could inform green of the information if needed. Etc. So this is simple, but it's a key to make a robot a little more pertinent in doing the task, etc. Another example that we have run in this, I mentioned the mall. The robot is able to compute the two perspectives. The robot here it's a pepper seeing the human. Here it has motion capture, but now we do not have it. And the robot is building the perspective of itself at your left and at the right of the human. So, for example, you can see that the robot computes that it is seen by the human. Okay? And what are the objects they can see? And based on this, the robot could track the human. This is what we are doing, etc. Okay? And do a number of things, computing where to put objects so that they are seen or visible or reachable to a human. Okay, so after that I have a number of slides, but I will stop here since I spent my time. And so I invite you to if you are interested, to look at what we can do based on this kind of behavior. But I wanted essentially here to bring the message of the model behind these issues, that essentially to show that in fact when you add the human, you enrich a lot the decisional problems of the robot, also the physical problems of the robot. Thank you. I should simply show this. I had a lot, as you see, but okay, I haven't shown everything. I finished. I just want to put the name of the people who contribute to this, because it's not fair. These are the people who contributed to this work here. I have not shown it, in fact, but the people who have contributed to this. And here, so all this is only for fetch and carry and manipulation. It's already very big and very interesting. And these are different criteria that could be taken into account when building these systems. I'm stopping here. Please. I have the light in front of the light, so I don't see. Now I see you.
Okay. Hi, Rachid. Thank you for this presentation. It was very funny and interesting and exciting too. So just regarding the scheme for joint action, actually, I was wondering if this scheme is a kind of, let's say, the best possible scenario. So that means, could it be, let's say, reduced a little bit, some of the elements, or all of them are strictly necessary for this interaction? Because I have the feeling, which is maybe I'm wrong, but maybe it's not necessary to have like if we have a good information about the memories of the other person, will be better for the action, but humans can, develop actions together without having sometimes much information about this. So this is my question: is this all the elements required?
No, it's a very good question. I tried to draw the large scheme. Okay. And now it depends, I would say, on the task that you want to build, the robot that you want to build, for which kind of task. There are some tasks and robots that do not need the full scheme. Okay? For example, if you have a robot that is simply navigating between humans, it does not need all this scheme. Okay? Because there is one only shared goal that is defined, which is not collide and do not disturb. Okay? Which is enough. Okay? For example, depending on which robot you want to deploy, which system you want to do, it could be different. Okay, same. You have other applications where the robot is static and doing nothing, essentially observer. Okay, or very very little. In a factory, for example, there are rules that are known and clear for everybody, and the human respects rules. Also, it's different from the robot at home, where the human is normally free at home and does what he wants. Etc. Okay, I would say, unfortunately, in the future, if the worker in the robot disturbs the robot, the worker will be fired. Okay, so there is an issue, but still, okay. So depending on the context, it will not be fully the same. But I think it is important to have in mind the full sketch.
Thank you, Rachid.
Any other question? Rachid, I thank you.
Thank you. Thank you.
Thank you very much, Rachid.